Introduction, Sampling and the Law of Large Numbers. In this lesson, we will explore how probability, sampling, and statistics connect. What is a sample? Why do we collect samples? How does a large sample help us understand a population? You will use Python to see these ideas in action. Running the cell now. Let us start by importing the needed libraries for working with data and making plots. Import important warning settings so we do not see distracting messages. Set warnings to be ignored for a cleaner experience. We are bringing in the libraries required to simulate data, organize data, and show graphs. NumPy helps us simulate numbers and probability. Pandas makes data easy to handle. Matplotlib helps us make charts. Running the cell now. Let us try running this to make sure everything loads. What is a sample? A sample is a smaller group taken from a larger population. We almost never see every possible person or event. By picking a sample, we can estimate what the whole population is like. Running the cell now. Let us imagine a huge jar with 10,000 marbles inside. Some marbles are blue, and some are red. Let us simulate what this giant population looks like. We are setting up a pretend jar with 10,000 marbles. Here, we describe how many marbles the jar has. We are saying that 60% of the marbles are blue. This line creates the big population. Each marble is labeled as a blue or the red according to the 60% chance. Let us check the total number of marbles to be sure. Let us peek at the first 10 marbles to see their colors. Running the cell now. Think, what would happen if we changed the prob_blue a value? Now let us see how many marbles of each color we have in the whole population. We want to know how often each color shows up in our jar. This command finds the unique colors and how many times they appear. We put the results into a nice dictionary for easy reading. Let us print the totals for blue and red marbles in the population. Running the cell now. Compare these numbers to our expected 60% blue marbles. Real life, why sample instead of measuring all? It is usually too expensive or impossible to check every single item in a population. Instead, we use samples to estimate things like winning vote percentages, how tall people are in a city, rate of a disease. The law of large numbers is what lets us trust our sample results. Running the cell now. Let us take a small sample from our population and see what colors we get. We are randomly picking only 20 marbles, without putting them back. Let us print out which marbles got picked. We show the sample so we can see the actual selection. Now, we count how many blue and red marbles we got in our sample. We pack the sample counts into a nice dictionary. Let us print the color distribution for these 20. Running the cell now. If you ran this again, would you get different results? Let us try sampling more marbles each time and watch what happens to the blue fraction. Let us see what happens when our sample sizes get larger. We will test with samples of size 20, 50, 200, and 1000. We take a sample for each size in our list. We calculate the fraction of marbles that are blue in every sample. Let us print how close each new sample comes to 60% blue. Running the cell now. Notice how larger samples give estimates closer to the true population ratio. The law of large numbers. The law of large numbers says, as you increase your sample size, your sample statistics, such as average or proportion, get closer and closer to the real values of the whole population. This is why surveys and experiments use enough data. Small samples can be noisy. Running the cell now. Now let us see what happens if we repeat taking large samples many times. We will make a histogram, or a bar plot, showing how the blue fraction varies from sample to sample. We are going to make 300 samples from our population. Each sample will have 500 marbles. We will collect the blue fraction from each big sample. This loop repeats the random sampling process a lot of times. It takes a new random sample on every loop. It measures the blue fraction in each sample. Each time, we save that result for later. Now, we make a histogram to display the spread of these blue fractions. The red dashed line shows our true blue fraction in the whole population. We label the horizontal axis to mean blue fraction in a single sample. We label the vertical axis to show how many times each blue fraction appeared. We give the plot a title that describes the idea. This puts the legend in the plot. Finally, let us see the chart. Running the cell now. Try changing the sample size to see how the histogram changes. You can pause the video and experiment. Let us let you pick the sample size. This helps you see how your sample result may change each time. Enter a sample size when prompted. Now you get to choose your own sample size. You will type in the sample size you want. We take a new random sample using your input size. We count the fraction of blue marbles in your sample. This prints your blue fraction so you can compare to the true value. Running the cell now. Practice, try different sample sizes and look at your results. What happens if you use a very small sample? A very large one? Sampling in real datasets. Let us see a real example using actual data. The Titanic dataset has information on over 800 people from the famous ship. We will sample from it, just like with our marbles. Running the cell now. Let us load the Titanic dataset using Seaborn. We will take a quick look at its shape and first few rows. We use Seaborn to load the Titanic dataset. This tells Python to open the Titanic data. Now we have our data loaded and ready to use. Let us print out how many rows and columns there are. This shows us the first few people and their details in the dataset. Running the cell now. Look at the data columns and guess which features may be useful for analysis. Let us pretend we only got to survey 50 random people from the Titanic. We will estimate the survival rate from this small sample and see how it compares to the actual value. We set the sample size to be 50. We randomly pick 50 people from the data set. Now, we calculate how many survived in our sample. We also check the actual survival rate in the full data. Let us print both the example and the real rate for comparison. This prints out our sample size so we remember what we used. This prints the sample survival rate. This prints the real survival rate for everyone in the dataset. Running the cell now. Try different sample sizes and see how close you get to the real survival rate. Now, let us repeat the sampling process 200 times. We will create a histogram showing how the sample survival rates vary from sample to sample. We will use a sample size of 50 for our experiment. Our plan is to repeat the sampling 200 times. We will collect the different survival rates each time. This loop makes a brand new sample every time. It grabs a random set of 50 people with replacement from the Titanic data. It counts how many survived, and records that number. We now make a histogram to see the spread of survival rates that we observed. The red dotted line shows the true survival rate from all data. We label the horizontal axis and vertical axis to explain the graph. The graph title reminds us what we are seeing. This adds the legend for clarity. And finally, let us see the chart. Running the cell now. Can you see the law of large numbers in action here? Mini project: build and analyze your own sampling simulation. Let us put it together. Your goal: simulate a population, draw samples, and show how sample statistics move closer to the population value as you increase sample size. Ready to try? Let us code next. Running the cell now. Let us simulate your own fruit population. You can picture this as 2,000 fruit, with most being apples. You will now create a pretend population with two categories. For this example, 80% are apples, and 20% are oranges. This line sets the total population to 2,000. 80% of them are set to apple. We fill the pretend fruit basket with apples and oranges according to our percentages. We print the total amount to double-check. Running the cell now. Now try sampling from this fruit basket in different ways. Try out different sample sizes from your population. Notice what happens as the sample gets bigger. Let us try out different sample sizes for our fruit basket. We will test with 5, 20, 100, 500, and 1,000 fruits at a time. For each sample size, we draw a random group of fruit. We measure how many apples there are in each random sample. We print out the size and the apple proportion. Running the cell now. Can you spot a pattern as the sample size increases? Recap: what did we learn? Samples are small groups from larger populations. The law of large numbers explains why bigger samples give more reliable estimates. Sampling reduces the cost and time needed to learn about a whole population. Want more practice? Try different population sizes or sample percentages. Running the cell now. Before you go, if this helped you, subscribe and share the video. Keep exploring. Data science is all about asking questions. Try using what you learned on your own data and see what patterns you find. Running the cell now.